Let's further discuss these training and predicting time complexities for our decision tree model. These time complexities, they can be abstract at times. Let's go ahead and use an example. Let's go ahead and examine a case so we can actually see what happens if we were to double our training points. So let's say originally we had a data set, or we trained our model with 1,000 observations. So our training set size is 1,000 observations. And we want to see what is the consequence if we were to double our training set in terms of how long is it going to train the model and how long would it take the model to make predictions. So we're going to go from 1,000 to 2,000 observations. Let's examine the first situation. How is that going to affect prediction time? Of course, we want a model that is quick to make predictions, so let's see the consequence. So the time complexity for prediction is log of n. Oftentimes with these time complexities, log, if you see log, it's assumed it's log base 2. So let me just be explicit there, log of base 2, but oftentimes that 2 is omitted. So we're going to go from 1,000 observations to 2,000 observations. Now remember that when we increase our training set size, what's going to happen is that our model will tend to grow, will tend to be bigger. Our tree will be bigger. And if our tree is bigger, then that means that there are more questions we must answer to make a prediction for an observation. If we look at the time complexity, we can just do a ratio. We can say, what is the ratio of log of 2,000 over log of base 2 of 1,000. Now I'm just going to approximate this. So log of base 2 of 1,000 is approximately 10. The reason why I knew that rather quickly is because 2 raised to the 10 power is 1024. So approximately speaking, yes, I can go ahead and do this exactly, but it's approximately 10. And the log of 2,000 is going to be approximately 11, because 2 to the 11 power is 2048. So just for this example here, it's just approximations. So if you were to double our training points, our training observations, then the model is not going to get that much deeper. So the prediction time is only going to increase about 10%. So this ratio is 1.1, so a 10% increase in prediction time. So if our prediction time is a second, now we have a prediction time that's 1.1 seconds. So not much of an effect. So we're rather insulated to increasing the training size with regards to prediction. That's great. Let's go ahead and examine the other situation. How will this impact our training time? This is very important because the longer it takes to train, then the longer it takes to tune the model. So let's go get a good idea of what's the consequence of training time. So in this example here, or for decision trees, we derive that the time complexity is n p log of n. And the convention we're going to use throughout this course is that for these time complexities, n is going to refer to our training size, the number of observations in our training set. And p represents the number of features we have in our model. So we see here is that if we increase the number of features, there's a linear response. With prediction, there is no consequences with changing the number of features we have in our data set. But as we double, if we were to double the number of features, anywhere from let's say 3 to 6, then our training time is going to double. So it's a linear response, a linear relationship between training time, and the number of features we have in our data set. Now let's consider the number of observations. So we have this term, n log of n. So the training time complexity with regards to the number of observations is n log of n. Let's go ahead and see the consequence. Once again, going from 1,000 observations to 2,000 observations. What would happen to our training time? So let's go ahead and do the math. So we can do the ratio. So we have 2,000 times the log of 2,000, which we discussed is going to be approximately equal to 11, divided by 1,000 times log of 1,000. So this would be 2 times 11 over 10. So approximately 2.2. So this factor is 2.2. So in other words, if we were to go from 1,000 to 2,000 observations, our training time will roughly double. It's going to more than double. It's going to increase by a factor of 2.2. So yes, the consequence here, or the conclusion here, is that the training time is not going to have a linear behavior. In other words, if we double our training size, our training set, we're not going to double our training time. So we double the number of observations. That's not going to double the training time. It's going to more than double, a slightly linear situation, a slightly super linear scaling. In this case, 2.2. So that's still, so you might be wondering, is this great? Is this bad? Is this good? How does this compare? Well, that's why we want to talk about these time complexities, such that when we talk about a different model, we analyze a different model, we want to consider what are the training and prediction time complexities, and how does it compare with other models. In an ideal world, of course, as you increase the training size, that has no effect on training and prediction, but we understand that's going to have a consequence. And this is going to factor in what's a good model to use. There might be a situation if we have a model that has a horrible scaling with a number of observations, then when we get to very, very large data sets, then perhaps it no longer makes sense to use that model. Maybe that model, yes, might have a better performance, but then we have to evaluate. Does it make sense to get that slightly better performance if it means that the training time is just too long, intractable? And if our training time is just too long, it's also going to be harder to tune the model. To explore all the different sets of hyperparameters is going to best tune the model. So with regards to the original question, is this good, is this bad? In general, this is pretty good. Yes, like I said before, it's not linear, it's slightly super linear, but that's pretty good. In fact, I will direct you to this website called Big O Cheat Sheet, and sometimes it's helpful to see the trends of these curves, these time complexities. So this website will show you the different, how these time complexities vary with the number of elements. You consider the number of elements would be the training size. You can see n log of n. If you look at it, it has a somewhat linear behavior, slightly super linear as we saw before, but in general a linear behavior. And if we have an n-squared, that's a pretty horrible. You can see how quickly that diverges with respect to n log of n.